Lesson 8-5 is kind of unique in that it summarizes all the types of functions we've worked with. So in the first semester, we worked with linear functions, and you probably remember them well, but if we look at inputting an x of -2 and getting out a -1, notice how our x values are just climbing up, stepping 1 over, 1 over, 1 over. Our y values are increasing by 2 each time. So it is an adding by 2 every single time. From 1 to 3, it's adding 2. From 3 to 5, it's adding 2. So our difference is adding 2. That first difference means if you were to find the change in each of the outputs, what's the pattern? If it's a linear function, your first differences are all the same or they're all constant. That's how if you get a table of values and you see that they are changing or adding and subtracting by the same thing every step, every time the x value changes by 1, and all the y values are changing by the same rate, then that would be linear. If we look at this function, notice how our x values, I just want to mention, are all going up by 1 in both of these tables. So that's important, but most times we're not going to trick you in this chapter. Let's look at 3, it jumps to 9. 9, it jumps to 19. 19 jumps to 33. So the first time, 3 to 9 has a difference of 6, and 9 to 19 has a difference of 10. 19 to 33 has a difference of 14. And then from 33 to 51, let's see, I went difference of 6. So difference of 6 there, difference of 10 there, difference of 14. It's going to have, so from 33 to 51, it's going to have a difference of 18 and so on. So notice how now we're going to do this again. This was not constant. These are not all the same number when I subtract these two. So I'm going to do this again. The difference from 6 to 10 is a 4. From 10 to 4, oh, now that's a 4. 14 to 18, that's a 4. Believe it or not, this is actually a quadratic function. This is a parabola. So now we see that the second time we take the differences, the second differences are constant. So quadratics are what we were just dealing with in this chapter. That means this table of values. Now you could plot it and get the idea that it's going to make a parabola, but that will make a quadratic. The one before would have been a line. Now let's see what's happening here. Again, our x values are going by 1. Our y goes from 1 to 2, 2 to 4, 4 to 8, 8 to 16. Hopefully you see that it's really doubling. And I'm hoping it brings up some ideas from lesson or topic 6 where it was exponential. And we can kind of cheat here and see that that is where we're headed. But let's do the differences. Difference means subtract. So 2 take away 1 is 1. 4 take away 2 is 2. 8 from 4 is 4, and 16 from 8 is 8. These are not the same, so it's not a line. We try again. From 1 to 2, it's a difference of 1. From 2 to 4, it's a difference of 2. 4 to 8 is a difference of 4. Again, we're just subtracting. We'll try one more time. A difference of 1, a difference of 2. Do you see how these columns of all the differences are actually looking like each other? They say that the ratios of the consecutive y values. Okay, we're looking at like what they're multiplying by. So the ratios are actually all the same. Again, so we're going to say they're not really constant, but they're the same. So if I would take 8 divided by 4, it's 2, or 4 divided by 2, it's 2. Here, 4 divided by 2 is 2. So the cool part about lesson 5 here is that if you get a table of values, you can determine if it's a linear, quadratic, or an exponential. Our x values are going by 1. Here I have, this is going, difference here of 3. It's going down by 3. This one goes down by 9. And this one goes down by 15 and -21. So it's not linear because those are not a constant decrease. So now this goes down by 6, and this one goes down by 6, and that one goes down by 6. Because our second difference is constant, that makes this quadratic. Now, let's try this one. 12 to 4 be 8. 36 to 12 to do a lot of mental math here. 36 to 108 is 72. And the difference here is 216, so it's certainly not linear. Now we can take the difference again here. One thing to note, you might notice that 4 times 3 is 12, and 12 times 3 is 36. I think it's fair enough that if you can see it's multiplying by the same number each time, we know it's going to be exponential. But I'll follow through here with this table rule to note that this difference is 32 and then 96. Okay, so how would we check if this is actually exponential? When you take 24 divided by 8, you get 3. 72 divided by 24, you get 3. By making ratios, or 96 divided by 32, you also get 3. Every time you take a difference ahead divided by the difference behind it, you would get 3. That will make it exponential. I personally think because they grow so quickly, you may be better off, and there's nothing wrong with just realizing that those y values are multiplying by a factor of 3 each time, so we'll call it exponential. One other thing you can do when you have a table and you look at what it's changing by each time, and you decide if it's linear or exponential, you can make an equation on Desmos. So first of all, to decide if it's linear, quadratic, or exponential, we're going to go ahead and find those differences and see what we think. It certainly doesn't seem to be multiplying, but let's check it out. Pattern is going down, so here we lost 10.5. Here we lost 10.6. Here we lost 10.5. Now, this loses 10.6. Sorry, I'm out of room there. But because it's decreasing by a pretty much steady number, this is actually real data. So not every table of data you collect in the real world is going to give you perfect changes. But since they're all pretty darn close to having your first difference be constant, we would say this is linear. So to get a regression equation, that means to have Desmos or a calculator make an equation for you to try to fit those points, we could go to Desmos and type in the points that we want. So we would start by inserting our table from this data. And if you want to see the points, hey, we can kind of tell that was linear. That's what's neat, is you can get a visual representation of it. So since we think it's a line and we want Desmos to make us an equation, we type our y1, because we want to use these y1 points up here, and the little tilde, mx1 plus b, because that's the general form of a line. Look how great that black line fits there. So we would say our equation comes from, here's our m value of negative 10.55 and our b value of 100. So our equation would be y equals negative 10.55x plus 100.02. That's the equation of the line that would best fit that data. And should you want further data to predict, you could plug in any x value you want into that location and find the y value that would likely go with it.